All engines failure. The all engines failure is the situation where the aircraft entirely or partially loses engine thrust, and is no longer able to maintain level flight. The all engines failure can be identified by the flight warning computer or by the flight crew. In most cases, the flight warning computer detects an all engines failure condition and displays the all engines failure ECAM alert. In some cases, the flight warning computer does not detect the all engines failure condition. In the case of partial loss of thrust, no engine flame out on one or more engines, the residual N2 may remain slightly above the engine fail alert threshold. Even if the all engines failure alert is not triggered, the flight crew must rapidly decide to apply either the all eng fail QRH procedure, or the emergency landing QRH procedure, depending on their assessment of the situation. If the flight crew considers there is sufficient time to attempt an engine relight, they must apply the all engine fail QRH procedure. However, if the flight crew considers there is not sufficient time to attempt an engine relight, they must apply the emergency landing QRH procedure. Technical background. An all engines failure situation mainly results in an emergency electrical configuration, and in the loss of the green and yellow hydraulic systems. Electrical configuration. In the case of an all engines failure, all the AC busbars are lost. The ram air turbine automatically deploys to supply the emergency generator. The emergency generator supplies both the AC essential and the DC essential bus bars. The AC essential shed bus bar and DC essential shed bus bar are supplied by the constant speed motor or shed, when the aircraft is supplied only by batteries. The emergency generator can supply all the electrical loads that are necessary for the remainder of the flight. The emergency generator, that is connected to the network, remains connected even if all the main generators are recovered following engines relight, or if the APU generator is connected. Below flight level 250, if the flight crew can start the APU, the normal electrical configuration partly recovers. APU start. If fuel remains, the flight crew should attempt an APU start regardless of the RAT type in order to recover cabin pressurization, additional electrical power, and have bleed available for a starter-assisted relight, if necessary. APU start attempts use the aircraft batteries and reduce batteries load. Each APU start attempt reduces flight time on batteries by about 3.5 minutes. Total flight time on batteries is more than 30 minutes. Hydraulic generation. The green and yellow hydraulic systems are lost. The ram air turbine automatically deploys to pressurize the blue hydraulic system. When the hydraulic power is lost, the right aileron is lost and goes to its zero hinge moment position. There is enough authority to balance this roll, but instead of flying with permanent stick deflection in roll, the PF may use the rudder trim to generate sideslip and therefore compensate for this upfloating aileron. When the APU generator is connected, the control of the right aileron is restored due to the recovery of ELAC2. As hydraulic power is only available from the ram air turbine, the PF should avoid large and rapid rudder deflections. If engine windmilling is sufficient, additional hydraulic power may be recovered. General philosophy. Following an all engines failure, the cockpit indications change significantly, because the generators disconnect from the AC and DC bus bars. AP, FD, and autothrust are lost. Aircraft operates in alternate law. CM2 PFD and CM2 navigation display are lost. When the flight crew detects an all engines failure condition, they must apply the golden rule: 1. Fly, navigate, communicate. In this order and with the appropriate task sharing. CM1 left-hand seat pilot is the PF since only PFD1 is available. CM1 must immediately take over control of the aircraft, and must establish a safe flight path. After the PF establishes a safe flight path, the PM should perform the ECAM actions. The EWD remains available. The PM-CM2 side can display the SD pages on EWD by pressing and holding the associated system page push button on the ECAM control panel. The all engines failure alert provides the first key steps of the procedure and then directs the flight crew to the QRH all engines fail procedure. Due to the advantages of the windmill relight available for a large altitude range, simultaneous relight attempts on all engines, relight attempts not dependent on the technical condition of the aircraft systems compared to the starter-assisted relight using the APU bleed, the all-eng fail procedure promotes the windmill relight for all altitudes of the certified relight envelope. As a result, the optimum speed for windmill engine relight is displayed on the ECAM when the all engines failure alert triggers. This optimum relight speed depends on the engine type and enables an immediate windmill relight without an excessive aircraft descent rate within the whole windmill relight envelope. Depending on the circumstances, in order to reach the optimum relight speed, the flight crew may increase the speed during descent. However, the flight crew should keep in mind that, in alternate law, the overspeed protection is lost and that the aircraft speed and Mach upper limits are reduced. If the all engines failure is subsequent to a flight through volcanic ashes, the situation may be associated to unreliable speed indications. Therefore, the QRH procedure includes complementary information compared to the ECA MOND provides the pitch attitude that the PF must maintain to target the optimum relight speed. The flight crew must set the thrust levers to the idle detent in order to avoid any thrust power surge when the engine relights. The gliding distance displayed on the ECAM enables to roughly estimate the aircraft range as a function of the aircraft altitude at the optimum relight speed without wind. As a result, the flight crew should be able to rapidly assess the situation and determine their landing strategy if the engines do not relight. However, this gliding distance figure is an envelope value. As a result, depending on actual parameters, the actual gliding distance may differ. After their range assessment, the PF should then initiate the diversion to an accessible runway, or determine the most appropriate area for a forced landing or ditching. When time permits, the flight crew must transmit an emergency message to ATC using VHF-1. Depending on the exact situation, assistance may be available from ATC such as position of other aircraft, safe direction, closest airport. Different causes may lead to a thrust loss so that altitude cannot be maintained. However, fuel starvation is one of the most probable cause. As a result, the QRH all-engine fail procedure requests the flight crew to check the onboard fuel quantity in order to ensure that the aircraft is not experiencing a fuel starvation issue that will prevent engines relight. Then, depending on the flight crew assessment of the situation, they must determine whether engines relights can be attempted, or not. The QRH, all engines fail procedure addresses all situations and provides all necessary procedure steps until the touchdown if the engines do not relight. As a consequence, the QRH procedure includes the ditching or the forced landing procedures adapted to the all engines failure situation. IF engine relight can be attempted. If the flight crew attempts an engine relight, the QRH all engine fail procedure provides all the necessary information and conditions to perform a successful engine relight. Windmill relight. In windmill, the flight crew tries to relight both engines at the same time. The engine master levers must be set to off for 30 seconds, in order to ventilate the combustion chamber of the engine between two relight attempts. If the combustion chamber is not ventilated, the following may occur: engine stall, or engine tailpipe fire, or not successful engine relight. After the flight crew sets both master levers to on, they must monitor the N2 and the EGT parameters, to check if the relight is successful. If the first relight attempt is not successful, the flight crew should repeat the windmill relight on all engines. Starter-assisted relight. However, below flight level 200, the flight crew can attempt a starter-assisted relight of one engine at a time, if none of the engines relight after windmill relight attempts, and the APU bleed air is available. When the APU bleed is used, the flight crew must fly at a speed below the optimum windmill speed, to enable a starter-assisted relight of the engines. The flight crew reduces speed to the green dot speed, to minimize the descent rate of the aircraft. The green dot speed with all engines inoperative is displayed on the CM1 PFD. However, the procedure, QRH, all engines fail provides a table of green dot speed with all engines inoperative, depending on the weight and altitude of the aircraft. When the APU bleed is used, the flight crew should only attempt to relight one engine at a time. The APU cannot provide sufficient bleed to relight two engines at the same time. Therefore, during the sequence of a starter-assisted relight, both master levers must not be in the on position at the same time. The flight crew only sets one master lever to on. Then, they must monitor the N2 and the EGT parameters, during at least 30 seconds. 30 seconds is the minimum time required to determine if an engine relight may be successful or not. It is also the time that is required for the ventilation of the combustion chamber of the engine, with the master lever off. After at least 30 s, as long as the N2 and the EGT continuously increase, and the engine parameters reach idle values but do not exceed the limits, the flight crew should not abort the relight attempt. Depending on the engine state and on the environmental conditions, the in-flight engine relight may require more time, when compared with an engine start on the ground. If there are no signs of relight, the relight is considered not successful. The flight crew must set the associated master lever to off, and try to relight one engine at a time regularly. To relight the opposite engine, the flight crew may immediately apply the sequence for engine relight one at a time, because the opposite engine is already ventilated. To relight the same engine, the flight crew must wait 30 seconds before they apply the sequence for engine relight one at a time, to enable the ventilation of the engine. IF engine relight cannot be attempted. If the flight crew considers that they cannot attempt engines relights such as engine damage, fuel starvation, they should apply directly the applicable section of the QRH, all engine fail procedure. This section requires flying at green dot speed, that is the best lift-to-drag ratio speed, in order to maximize the remaining time for cabin preparation and distance flown. This section of the QRH, all-engine fail procedure provides a table of green dot speed with all engines inoperative as a function of the aircraft weight and altitude. If fuel remains, the flight crew should start the APU below flight level 250 to improve electrical power supply and recover CM2 display units. The flight crew should also use APU bleed below flight level 200 to recover the cabin pressurization. Approach and landing. When conditions permit, the flight crew should continue engine relights attempts using the APU bleed. If no engine relights, and depending on the situation, the flight crew should prepare the aircraft either for a ditching, or for a forced landing, even if a runway can be reached. Ditching and forced landing procedures are very similar, except for the landing gear that must be up for a ditching. The flight crew should pay attention to the time to manage the QRH procedure. An efficient procedure application is important to fully configure the aircraft for the ditching or the forced landing. Some items at the end of the procedure are time-consuming, such as slats extension. The flight crew must notify the cabin crew of a forced landing or ditching, in order to prepare the cabin. For approach, only slats are available. Forced landing. If the flight crew expects a forced landing, they must extend the landing gear to absorb some energy at touchdown, even if the landing is planned out of a runway. The landing gear must be extended by gravity. Since the trajectory is significantly modified when the aircraft is configured for landing due to slat, flap and landing gear extension, the descent slope is provided at the beginning of the forced landing section of the procedure to help flight crew anticipate this modification. For the PF, during the initial and final approach, the main concern is the aircraft energy management. The PF should maintain aircraft path higher than in a normal approach because there is no engine to manage energy. If the aircraft is too high to reach the landing area, the PF may use the remaining speed brakes to generate drag and increase the descent rate, if needed. When the flight crew selects a runway, they may perform a visual approach, if possible. When on ground, the flight crew can use the brake pedals. The brake accumulator provides the hydraulic power to the brakes, but the number of brake applications is limited. As the anti-skid is not available, the brake pressure should be limited to 1000 psi. As the nose wheel steering is lost, the PF must use the rudder at high speed in order to maintain the runway axis, if applicable. At lower speeds, the PF may use differential braking to maintain the selected axis but avoid brake release for accumulator endurance purpose. Ditching. Just before ditching, the flight crew must set the ditching PB to on in order to close all valves under the aircraft. Then, the flight crew must touch down with a minimum aircraft vertical speed. The flight crew should maintain the optimum pitch flare until the impact on the water, and should keep the wings level. Relight of one engine. When at least one engine relights, the all engines failure alert disappears and the engine fail alert is triggered on the EWD for the remaining engines. The engine fail procedure requests to consider the application of the QRH engines relight in-flight procedure. The QRH engines relight in-flight procedure enables to attempt either a windmilling start or a starter-assisted engine relight with the bleed of the other engine. The flight crew can decide at any time to stop the QRH engines relight in-flight procedure if the situation requires, such as remaining time and distance to fly, and to continue with other ECAM alerts or QRH procedures, if any. When at least one engine is recovered, AC1, DC1, AC2 and DC2 are recovered and normal electrical configuration is restored, except that AC essential bus bar and DC essential bus bars remain supplied by the emergency generator. When at least one engine is recovered, green, yellow and blue hydraulic systems are restored. Green and yellow systems due to the engine and associated engine-driven pump recovery, and the other hydraulic system by means of the PTU operation. Blue hydraulic system is recovered as the electrical supply of the blue electric pump is restored.